Welcome, ladies and gentlemen. This is going to be your note guide video for section 6.1, which is all about right triangle trigonometry. This is definitely a blast from the past from your geometry course with a little bit of added nuances, which is great. So enjoy the review, but also appreciate the new material as well. I'm going to say that this part in general is going to be what we're going to label as Part A. We're breaking this section 6.1 into two parts, Part A and Part B, where the first page here is going to be your Part A. So here we go. Our objectives here are identify and use the 6 trig ratios, and the second is to solve right triangles. And the first part here is getting into the six trig ratios. Which I'm going to kind of remind you when you have a right triangle, if this right here is the angle you're focusing on, which we're going to call theta, this is theta, the side directly across is called the opposite, the side touching that angle is adjacent, and of course the side directly across from the 90-degree angle, or the longest side, is the hypotenuse. You would have learned a mnemonic last year, SOHCAHTOA, where SO stands for sine is equal to the opposite side over the hypotenuse. So you're talking about the length of the opposite side over the hypotenuse. These are all ratios of side lengths. So that is going to be your sine of any given angle would equal to the ratio of the side lengths of the opposite over the hypotenuse at that angle. Cosine is adjacent over hypotenuse, and then the tangent is opposite over adjacent. Yay, so all this is nothing you haven't seen before, but over here, this cosecant, right here, this stands for cosecant, this is secant, this is cotangent. I know when I've taught geometry, we introduce those, and what we talk about is how they are inverses of sine, cosine, and tangent, and I will just mention that these are inverses. And when we're talking about inverses, we're talking about really the reciprocals of the sine, cosine, and tangent function. So let me just first of all erase this so that's out of the way so it's nice and clean. And I'm going to say again that cosecant, notice I had put it right next to the sine. That's because the relationship here is that cosecant of any angle theta is equal to 1 over sine of that angle theta. And what's interesting about that then is if you're talking about that cosecant theta is equal to 1 over sine theta, that also implies then that cosecant of any given angle is going to be equal to the ratio of the side length of the hypotenuse over the opposite side. So notice they are going from here to here. These are reciprocals of each other. And you'll notice that that same pattern applies as we move across. So cosine of theta we knew is adjacent over hypotenuse. So secant of any given angle theta is going to be 1 over cosine of that angle. And then added to that is going to be the relationship of the side hypotenuse over the adjacent side. So they are inverses of each other. And maybe it wouldn't be bad to mention the word reciprocal over here. Reciprocal. So they are inverses or reciprocals of each other. Inverses. I lost my E there. Cotangent. Now I'm going to say that when I was in your spot, I always thought, oh, couldn't they have put sine of theta along with secant theta because they both start with the letter S? No, that would be too easy in math, right? So I'm just letting you know the way I always remember it is sine goes with the one that starts with the C, which is cosecant, and then the C one, cosine, goes with the one that starts with an S, secant. It's not pretty, but it works for me. So maybe you have a better mnemonic that you can kind of tell me about, and I'll share it with others. Tangent, cotangent kind of sound similar, so those are a little bit easier. So this is going to be 1 over tangent of theta. And then to finish up that idea, this is adjacent over opposite. So these are really, really, really important, and you will know them by heart, and you will continue to use these into pre-calculus, all the way into calculus and beyond. So important ideas. So let me just show you how these work. So example number 1, and this is a classic ACT question right here, by the way. It's evaluate the 6 trig ratios of the angle theta if A is 4 and C is 7. So we don't know this angle, nor do honestly we care what that angle is, but because it's not asking for that, it's asking what the ratio of the side lengths are. So we know that A is equal to 4, and we know that C is equal to 7. The thing they're not giving us is that B value. And since we have 2 of the 3 side lengths, we can use Pythagorean theorem really easy to find that length. So I'm going to go a squared plus b squared equals c squared. So again, coming back from the geometry days, my a side is going to be 4 squared plus my b squared equals 7 squared. So I have 16 plus b squared equals 49. When I subtract those, I end up with 33. When I take the square root of it, I end up with a b value of square root of 33. And square root of 33 cannot be simplified. Now if it were like the square root of 20, you would simplify it and go from there, but square root of 33 is it. Okay, so then what do we do? Well, let's the first thing you want to know is all 3 side lengths, which we do have. Now let's start talking about the ratio of those side lengths. Sine we know is opposite over hypotenuse, so we're going to put 4 over 7, which is the opposite side over the hypotenuse. And then I'm going to seek out the inverse of that. So I know that sine theta and cosecant theta are related. These two are related, and they are inverses or reciprocals of each other. So I can right away just say, hey, you know what? Then I know this one is 7 over 4, which is hypotenuse over opposite. And again, just a reminder, and you should have this down in your belt, but this is the opposite because it's directly opposite of the angle that we're talking about. But I feel like I have to say it still. Cosine. Cosine is going to be adjacent over hypotenuse, so I have square root of 33 over the hypotenuse of 7. Now the secant is the flip of it, is the reciprocal of it, but you know from first semester Advanced Alg that you cannot have a square root in the denominator. So I'm going to do the reciprocal right here, 7 over square root of 33. But then I need to rationalize, and we rationalize by multiplying the top and bottom by whatever that square root is, and I know it's kind of messy here. But ultimately, I get an answer here is 7 square root of 33 over 33. And again, rationalization was taught in Algebra 1, also in geometry, but also first semester of Advanced Alg. So I just kind of am using a tool you already know. So no square roots in the denominator. So I'm going to do a little bit of erasing so it doesn't look so nasty. You leave your work on your paper. I just don't have as much space because I write kind of big. So secant of theta is 7 square root of 3 over 33, and we need to make sure we rationalize this. And I'm just going to rationalize. And I'm really very vocab is just so important, so you'll notice I like writing those words down so you see them in addition to using them. Okay, so tangent of theta, opposite over adjacent, so we're talking about 4 over square root of 33. Again, if we rationalize it, we end up with 4 square root of 33 over 33. And you could do that longhand if you want, but when you're talking about opposite over adjacent, it's going to be this side over that side, and then you'll have to rationalize it just like we did with the secant. The cotangent, we can start from the original. Actually, I would highly recommend in this case to not, if you've rationalized a ratio, make sure you don't use that as just the reciprocal. You want to maybe go back to the triangle and say, okay, cotangent of theta is going to be the adjacent over opposite. And if I look over here, the adjacent side is square root of 33, square root of 33 over 4. Then you don't have to do any more work. So I'm just saying that otherwise it's going to get you can't have square roots in the denominator, but if you've already rationalized, let's say the tangent, don't just flip those, because then you'll end up with another square root in the denominator. So again, you'll end up with square root, oops, I have to switch this over, square root of 33 over 4. Okay, so that in a nutshell is how you find the 6 trig ratios of any given angle, knowing all 3 sides of the right triangle. And keep in mind, again, if you don't have all 3 sides of the right triangle, you need to find them using Pythagorean theorem or some other tool you have from geometry, whether, again, it's using SOHCAHTOA and so on. Now, notice this example 2 here. It says, let theta be an acute angle in a right triangle, so very similar. Find the values of the 5 trig ratios if theta, not 6 ratios, they're saying 5 ratios, because they're telling you that the secant of theta is already square root of 5. So I already am given this right here, which is super, super cool, because I know that if I take the square root of 5 and put it over 1, I have a fraction, which of course is a ratio. And now you can look back up at the top if you want, or you know that secant is associated with cosine. Cosine is adjacent over hypotenuse, so this means that this one is hypotenuse and this one is the adjacent side. So I'm going to come over here to this right triangle. This is the theta right there. And if we're talking about the hypotenuse, we know that's directly across from the 90-degree angle, or the longest side, which is square root of 5. And the adjacent side to this theta is 1. Now, I cannot find the other 5 ratios without having, actually I shouldn't say that, I could find cosine right away, because all I have to do is flip it, right? I can say, hey, cosine of theta is 1 over square root of 5, and of course we'd have to rationalize it by multiplying the square root of 5 on the top and the bottom. My handwriting is horrible, isn't it? Anyway, so it's square root of 5 over 5. There is the cosine of theta. Now, with that said, you can't do the sine, cosecant, tangent, or cotangent until you have this third side. Use your Pythagorean theorem. Find out what the side is right here. So you need to find this using Pythagorean theorem. And then at that point, then you can do sine, cosecant, tan, and cotangent. That, my fine young ladies and gents, will be something I look at when you come in and check it in with me. So I'm expecting you then to take it from there and show proof that you're understanding the material. Okay, so that is the end of my part A for section 6.1. And when you're ready to do section 6.1 part B, tune in. Any questions you can ask me in class, and thank you for tuning in.